Hello everybody. Today I'm going to be doing something a little bit different, and I'm going to be doing a sort of live solve of the Cambridge 6th term examination paper, or STEP, the STEP exam, which is essentially just a college placement test. Now, as you can see, the test is allotted 3 hours, but it's split up into 3 sections. So the first section is pure math, which essentially just entails like calculus based topics. Sorry, I can't spell calculus. And a lot of the questions from what I've looked at basically entail, they give you some fact, and then you have to use the fact and your, the calculus and algebra skills that you know to arrive at something else. So they're pretty interesting problems. The second part is actually physics, so it deals with classical mechanics. And the third part, I guess part C, is dealing with probability. Now, of course, I'm not going to be solving the entire test. I'm just going to be focusing on this first part, the pure math, since that sort of leans towards more of what my channel is about. And I have not looked in depth at these questions before, so this is going to be sort of a live solve. And so I'm estimating that this video will be about an hour long. Of course, given that I'm not going to go too in-depth into how to solve the problem, right? Because I haven't solved it before. It's just going to be sort of me, I guess, streaming my thought process on these problems. So without further ado, let's get into it. Okay, so we have a line, a squared x, and the curve, so we have a cubic, intersect at the origin. Yeah, that makes sense. And at 2 other points, x-coordinate of p is less than the x-coordinate of q. Okay, so this first part is saying to find the coordinates. So basically find the points where a squared x intersects x b minus x squared. Now, of course, we have this common factor of x, so we can just divide out by x, since we're already given that they intersect at the origin. And this just leaves us with squares on both sides. So we can write x minus b is plus or minus a, so x is b plus or minus a. Now, a and b are both positive, right? So, so p, the x-coordinate is going to be the smaller one, so b minus a, and the y is just going to be, we can plug it into either equation. So here I'll just plug it into the linear equation because it's simpler. And q is going to be b plus a, and a squared times b plus a. And then it wants us to graph, sketch the line and the curve on the same axes. So just imagine we have something like this. So this is y is a squared x. Now, this cubic, I'm not sure how to deal with. Of course, b minus a, since b is greater than a, b minus a is going to be positive. So p and q are going to be like sort of right here. So I'm imagining something like this, I guess. I'm not really sure, because go up and down and up. Something like that. Right. Okay, the next part of the question is show that the equation of the tangent to the curve, so of course it's talking about the curve x times b minus x squared at the point P, right? So let's see, this is the work for 1, so I'll just sort of box this off. So of course we have to take a derivative. If we take a derivative, use the product rule here, and then 2x, or I guess we get a minus 2x b minus x. And I'm actually going to take that minus, right, like that. And then, since this is squared, I just, well, I guess, I mean, they have a purpose for that, but I just prefer looking at it like this. So this is the derivative, and actually I'm going to factor out an x minus b term here, because we can. We get x minus b plus 2x, so that's 3x minus b. Now we plug in x equals b minus a, x equals b minus a, because that's at the point P, and so our slope is going to be, we get a minus a, and then 2b minus 3a. So that's going to be a times 3a minus 2b. Just flipping the terms. So this is our slope, right, m, right? And so we want y equals mx plus b. And so we just have to plug in, again, this point. So we have to have that a squared b minus a equal to a times 3a minus 2b. Although I guess I shouldn't use b here. I'll just write k, I guess. Alright, times our x value. Our x value is b minus a plus k. Okay, so okay, so then we solve for k, we subtract on both sides, there's a factor of b minus a, and then we get a squared minus 3a squared is 2ab. So this becomes 2ab minus 2a squared, which of course you can pull out a 2a here, and then you get another factor of b minus a. And so the tangent has the form, which is what we wanted to show. Note that this tangent meets the y-axis at r, right? So that's going to be, this is r, or I guess r would be, if it's saying a point, yeah, then it would be just like 0, comma, this value. The area of the region between the curve and the line segment OP is denoted by S. Huh. Okay. So now we have some integration to do. And the line segment OP. Well, the line OP, right, is just this line a squared x. So what we have to do is integrate the difference of the curves from 0 to our point P. So let's see what that'll be. Okay, so we're gonna have to expand this out a bit. B squared minus 2bx plus a squared minus a squared x dx. So we have b squared minus a squared x minus 2bx squared plus x cubed dx. And that's going to give us 1/2 b minus a squared, b squared minus a squared, minus 2b over 3b minus a cubed, plus 1/4 b minus a to the 4th. Okay, now they want us to show that this all has a factor of, well, b minus a cubed, right? So we have this b minus a cubed here, we have a b minus a cubed here, well, b minus a to the 4th, but there's a b minus a cubed factor, and then this difference of squares is going to give us another b minus a. So let's take out that, that b minus a cubed, and let's see what we get. We get 1/2 of b plus a minus 2b over 3 plus 1/4 of b minus a. So this is b minus a cubed. So collecting terms of b, we get 1/2 minus 2/3 plus 1/4. So in lowest terms, this is 12ths, so we have 6/12 minus 8/12 plus 3/12. So that's all going to be 1/12. So I'll just write 1/12. And then collecting terms of a, we have 1/2 and a minus 1/4, so that's just going to be 1/2. No, okay, I knew, yeah, there we go, I made a mistake. That's going to be a 4th, right, or 3/12, right? So this is gonna, we can factor out the 12. We get a b minus a cubed, and we get 3a plus b as desired. And so I'll write this as 3. And then finally, what we want is the area of triangle. So let's say this is R, this is P, this is O, OPR, denoted by T. We want to show that S is greater than 1/3 T, right? Okay, well, we can calculate this triangle area very simply. Right, so the area of OPR is gonna be 1/2 times b minus a. So 1/2, we can consider this to be a height of the triangle, right? And then the base is gonna be where R is, and that's 2a b minus a squared. So that's a times b minus a cubed. Then 3 times that equals 3a b minus a cubed. which is going to be less than 3a plus b times b minus a cubed. Let's see, wait. No. Okay, so what I want to do is, so 1/3, which is 1/3, and this is going to be, I'll just write it in terms of 12ths, 4/12ths. 4a is equal to 3a plus a, and since b is greater than a, this is going to be less than 3a plus b. So there we get 1/12 3a plus b, which is s. And that's what we wanted to show. So that's the first problem complete. And this is probably already going to be a long video. Okay, so okay, I don't like the way they have these like intermediate parts and then actual labeled parts. So if like express c and show that. Okay, so this is basically just showing the change of base formula for logarithms. So that shouldn't be too bad. So c is going to be b to the x. So we want to show that. So this is x, right? So then log base a of c is going to be log base a of b to the x, which is going to be x times log base a of b, right? Because you can take powers out of logarithms. So when you divide by log a of b, they're going to cancel out and you get x. So that's going to be the proof for that part. Okay, so the next part says, given that pi squared is less than 10, prove that this inequality is true. So we can write this as ln pi over ln 2 is 1 over ln pi over ln 5. And it doesn't really matter, I'm just using ln because it's shorter. This is going to give you ln 2 over ln pi plus ln 5 over ln pi, and that's ln 10 over ln pi, which is log base pi of 10. And since 10 is 10 is greater than pi squared, so this is going to be bigger than the log base pi of pi squared, which is equal to 2. Alright, now given that log base 2 pi over e is greater than a fifth. Okay. Interesting. So I'm smelling some log base 2 trickery. So the log base 2 of pi over e is going to be the log base 2 of pi minus the log base 2 of e. And if e squared is less than 8, that means that 2 log base 2 of e is going to be less than 3. So we can write that as log base 2 of e is less than 3 halves. Now ln pi, so this is greater than a fifth. ln pi is log base 2 of pi over log base 2 of e. And if we replace this by something by something bigger in the numerator, then it's going to become smaller. Or sorry, bigger in the denominator, it's going to become smaller. So we can put 3/2 there. And then log base 2 of pi is going to be greater than oh wait, no, so what I'll do is this is going to be bigger than 1/5 plus log base 2 e over log base 2e, which is 1 plus 1 over 5 log base 2e. And then that is going to be bigger than, we can replace this by 3/2, and you get 2 over 15, and that's going to equal 17 over 15. Alright, given that e cubed is greater than 20, pi squared is less than 10 again, and log base 10 of 2 is greater than... Okay, this is interesting. So we're sort of creating an estimate for the natural log of pi. So the log base 10, so this is going to give us 3 log base 10 is greater than 1 plus log base 10 of 2, which is greater than 13 over 10. So the log base 10 of e is greater than 13 over 30. And then if we apply log base 10 pi, that's going to be less than 1/2. So the natural log of pi, which is the log base 10 of pi over log base 10 of e, is going to be less than 1/2 over 13 over 30. And remember, these signs are justified. The numerator, it follows the same sign, and then the denominator follows the opposite sign. So this is going to give us 15 over 13. Right. So pretty fun problem overall. On to the next one. We have some geometry. So we have these points on the x-axis. A is greater than 0, the point P is coordinates x, y, x is less than 2a. Okay, so let's quickly draw a sketch. So we have A, right? Let's say like roughly like that. So this is going to be S, this is going to be R. Now we have P. P is going to be somewhere here, just in this, sort of to the top left of S, right? So this is P, so PRS is alpha, and PSR is beta. So we're going to show that if beta equals 2 alpha, then P lies on the curve y squared equals 3x squared minus a squared. Okay, so okay, so this is the origin. 2 alpha. Okay, so clearly if P is like over here, then like, okay, let's consider P is right here. Then like I'm trying to show that X can't be negative. Okay, for the moment, let's assume X is positive. So we have Y. This is alpha. We have Y and X plus A here, and then we have 2 alpha. We have Y, and we have 2A minus X here, right? So we have a simple tangent relation. So tan of 2 alpha is 2 tan alpha over 1 minus tan squared alpha. So what this means is that y over 2a minus x equals 2y over x plus a over 1 minus y over x plus a squared. Now y is greater than 0, so we can cancel that out here. So that simplifies things a bit. We could multiply both sides by the top and bottom by x plus a squared here. That's going to give us 2x plus a over x plus a squared minus y squared. And then x plus a squared minus y squared is going to equal 2x plus a 2a minus x. Okay, so this leads to that. I'm going to flip a sign here, so y squared, and then I'm going to expand out to x plus a x minus 2a, which is 2x squared minus 2ax plus ax, so minus 2ax, and then minus 4a squared. So the minus 2ax cancels, and we get y squared is equal to 3x squared minus 3a squared, which is 3x squared minus a squared, which is exactly what we wanted to show. And I think, yeah, even if x is negative, these lengths still work. But at the point where x reaches negative a, then alpha is gonna be like 90 degrees, right? So it will be impossible for beta to be equal to 2 alpha at that point, simply due to the sum. I mean, that's just going to force beta to be greater than 180 degrees. And we know at the very least that the sum of all three angles in a triangle is going to be equal to 180 degrees. So that's absurd if one of the angles is over 180. So we know, we can deduce that if beta is equal to 2 alpha, then negative a is less than x. And so this tangent argument holds. So that's part one. Now we want to show the converse. If alpha is between 0 and pi, and p is on this curve. Now, so let's think. Clearly we could work backwards here. This is a tough question. I think for, I guess, time of the video's sake, I'm just gonna go on to the next question. Okay. So f is defined as, let me zoom in a little bit, it might be too small. F of x is 1 over x ln x. Show that when ln x squared is 1, both f of x equals 0 and, well, okay, so clearly if ln x squared equals 1, then you have 1 minus 1, right? So f of x is going to be 0. Now on the other hand, f prime of x is, well, let's momentarily call f of x g of x times h of x, where this is g and this is h. So f prime of x by the product rule is g prime of x h plus g of x h prime of x. Now we know when ln x squared is 0 that h of x is 0, so this part's going to disappear. And then in the derivative of h prime of x, you're going to have 2 times 1 minus ln x squared times the derivative of this term. But this term is going to be 0, so this part also goes to 0. So we have 0 plus 0 is 0. Next off, we have this function, which is defined as a interesting piecewise integral. So this is defined for positive x values. So for x between 0 and 1, we integrate from 1 over e to x. So notice this could be a backwards integral. And for x bigger than 1, we integrate from e to x of f of t. So this could also be backwards. Find f of x explicitly. Well, okay. So essentially we just have to find a way of integrating like we have to explicitly integrate this. Now h, as I've denoted up here, is the more complicated part. So okay, well, let's just go for the most natural thing is going to be let u equal ln x, because then du is going to be 1 over x dx. So that gets rid of this 1 over x, and we have 1 over u times 1 minus u squared du, and this just becomes polynomial. Or at least, well, with this 1 over u still, we get a minus 2u squared, so that becomes a minus 2u, and then plus u to the 4th, that becomes plus u cubed, du, this becomes ln u minus u squared plus u to the 4th over 4. And so that's going to be ln x minus ln x squared plus ln x to the 4th over 4. Now now we need these absolute value bars here because ln of x can be negative. And of course we did an anti-derivative, so we have a plus c here technically. So when we take x, so let's suppose x is in this small region from 0 to 1. So so basically we just have to plug in 1 over e and e. So 1 over e is going to give us ln of ln of 1 over e. That's negative 1, so the natural log of 1, which is 0, minus negative 1 squared, that's minus 1, and then plus minus 1 to the 4th over 4. That's going to be minus 3/4. And then for e, we're going to have 0 minus 1 plus a 4th, which is minus 3/4, right? So at these endpoints, right, you're going to have the same thing. You're going to have f of x is ln x minus ln x squared plus ln x to the 4th over 4 plus 3/4. And of course you have it defined for these two separate boundaries, or these two different conditions, right? But the important thing is that if x is in 0 to 1, then then 1 over x is going to be in x greater than 1, and vice versa. If x is greater than 1, then 1 over x is going to be in between 0 and 1. So if we do this, 1 over x minus 1 over x. Basically, the important part is that this is a function of ln of x, and it is an even function of ln of x, primarily because of these absolute values and these powers, these even powers, right? So this is going to give us a negative ln x, but we take an absolute value, so it just becomes ln x again. This is also going to give us a negative, but we square it out. And this is also sorry, there should be 1 over x here. This is also going to give us a negative ln x, but we square it out. So everything remains the same, and these two conditions are essentially homeomorphic or isomorphic, or I guess there's no structure to them. There's a bijection between them given by 1 over x. That's what I'm trying to say. And since f of x preserves these negative signs, or gets rid of these negative signs, we have f of x inverses f of x. Now, this last part is telling us to sketch the curve of f of x. Now, hell if I know how to do that. I don't even know, something like that. Just looking at the function. These graphing parts are kind of tough. Alright, write down the most general remainder 1. Okay, well that's just 1, 8, 6, polynomial is degree n. Well, p of x has to be of this form above. X minus 1 dot 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 x minus n, because this is nth power. So p of n plus 1 will equal a times n factorial plus 1. And of course a is not 0, because this is a nth degree. If a was 0, then this would be a constant function, but p of x is nth degree, so a is not 0, so this is not equal to 1. Given that p of n equals 2. Okay, so we are given that p of n, so we're given that a times n factorial is equal to 1. So a is equal to 1 over n factorial. Then p of n plus r is gonna be 1 plus r plus r minus 1. Now this is reminiscent of a combinatorial thing. This would be 1 plus n plus r minus 1, choose n. And then it says find in integer r independent of n such that p of n plus r is n plus r. Sorry, I had to check that I was still recording. That would have made me a little upset. This is equal to n. Now, this binomial coefficient is symmetric, so we can read it like this. Yeah, so essentially this binomial coefficients satisfy this relation. So if r minus 1 is 1, then we have this. So that's pretty nice. Polynomial S of x. It satisfies. No integer e such that. Okay, so S of x is 2001 plus x minus a, x minus b, x minus c, and x minus d. Now, a, b, and c are all distinct integers, not necessarily positive. They're all different, though. Now, we want to show that you can't pick an integer such that this is 2018. So you can't pick an integer such that 17 is equal to e minus a, e minus b, e minus c, times e minus d. Now, I would assume that it has to do with 17 being prime, right? Because these are all going to be integers, and they're all distinct, so you can't have 4 distinct integers that multiply to 17, because the best you could have is 3, where you could have, or not even, the best you could have for distinct integers is like 17 times 1, right? Now you could have -1 times -1, but then you have a repeat. It's just simply not possible for these 4 to be distinct. And this is prime. So one of these is going to have to be plus or minus 17. The remaining 3 are going to have to multiply to plus or minus 1. So they're all going to have to be plus or minus 1. And of course you have 3. One term is plus or minus 17. The remaining multiply to plus or minus 1. So via pigeonhole, we have a contradiction, right? Because if they multiply to plus or minus 1, you can't have 3 distinct integers that do that, right? Because the only factors, integer factors of plus or minus 1 are plus or minus 1, so you could only have plus 1 and negative 1. A third integer would have to be a repeat. Contradiction. Find the number of ways. Okay, so here we have a combinatorics problem. So we have 16 is E. So 0. Okay, so 16 is A, B, C, D. Perfect. Okay, so A, B, C, D. So I guess we could just list out the integer factors, which is nice because this is a prime power. Right. So let's say we picked A to be negative 16, then BCD would have to multiply to negative 1. We can't do that for distinct integers, so negative 16 is out of the picture. Now suppose we picked a negative 8, and we needed something to multiply to negative 2, then we could do negative 1, 1, and 2. So that's one path. I'm just going to tally up. Next, if A is negative 4, then these have to multiply to negative 4. We could have... we have to have one negative, right? So we could have B, C, D, right? And that's the only way. Or we could have B, C, D. So that gives us two possibilities. Next, if A is negative 2, then we have negative 8. So we have to have this B here. And then the remaining multiplied to 8. So you could have 1 and 8 or 2 and 4. So that's another 2. Now A can't be negative 1 because then these have to multiply to negative 8, but then there's no negatives to choose from. So let's say A is 1. Then you have to have 16. And I don't think that's possible, because at that point there are simply the numbers multiplied to be too big. So this is all, just five possibilities. Okay, use the identity to show that. Okay, so this is kind of classical telescoping sum, right? So this is going to be 2 sine theta is going to be cosine 0 minus cosine 2 theta, right? And that's where this 1 comes from. Next, 2 sine theta sine 3 theta is going to equal cosine 2 theta minus cosine 4 theta. Then the cosine 2 thetas cancel, and so on. So this is just a telescoping sum. Alright. Let A sub n be the approximation to the area under the curve y. So we have 0, pi, this is sine of x. Midpoint of the top of each strip lies on the curve. I'm bad with drawing these sorts of things. Pi over n, 2 pi over n, 3 pi over n. So if it's the midpoints, then you have pi over n sine pi over 2n. And really this is going to add up. So a sub n equals pi. And then I see. So this is going to give us, and then over here you have n minus 1, n. So this is going to be 2n minus 1 pi over 2n. And then when we multiply by this pi of 2n, we apply the above rule. And so we get, so an sine of pi over 2n is we get pi over n times 1 minus cosine of 2n times pi over 2n. Oof, where did I go wrong? There's this 2 here. There's this missing 2. So if we divide, then we get 1 minus cosine 2n theta over 2. So what we have is we have that over 2 missing. This is 1 minus negative 1. That's 2. So this cancels. We get pi over n. Okay, let b sub n be the trapezium rule. Alright, so if we draw our curve again, so b sub n is going to be pi over n times, so the first area is going to be like 1/2 sine 0 plus sine pi over n, and then -1 and pi sine of pi. So what happens is we can ignore these endpoints since they're 0, and then we have all these 1/2s that add up. So we essentially just have sine of pi over n plus dot 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 plus sine of n minus 1 over n pi. So what happens is if we were to multiply by 2 sine of pi over n by this, we would get, using our collapsing rule, we would get 1 minus cosine of pi, so which is 2. Yeah? But, so divide this. So if we were to multiply, so essentially b sub n sine of pi over n is going to be pi over n. But sine of pi over n is 2 sine of pi over 2n cosine of pi over 2n. So did I goof somewhere? I see. So I can't apply this quite yet. So what's happening here is that this sum doesn't progress the same way. So the sum goes from pi over n to, let's say, 2 pi over n, right? But we need a progression of 2 theta, So in that case, theta would be pi over 2n. But we also have to start at sine of theta. So I guess it wouldn't hurt to just directly multiply and do the calculation again. So b sub n sine of pi over 2n is going to be pi over n. And what I mean by that is just cosine. And then when we get to this term, and we add 1 over 2n, well, we would get minus cosine of 2n minus 1 over 2n pi. And the rest telescopes. Of course, we have to be multiplying by 2, so we have it divided by 2 here. And then the cosine, if we look at a unit circle, the cosine reflects itself negatively across, so this is going to end up being pi over n cosine pi 2n. So what I mean by that is that cosine of 2n minus 1 over 2n pi is equal to negative cosine of pi over 2n. But we have this minus sign, so that contributes an extra term, cancels with the 2, and we get exactly what we want. Now the third part is to show a couple more things. So we want to show that the average, the average an and bn is equal to b sub 2n. So what I'm thinking is that if we multiply well, we sort of have explicit forms, right? So this is going to be 1/2. I'm going to take out a pi over n, so we get pi over 2n. We get 1 over sine, so that's cosecant pi over 2n plus cotangent pi over 2n. And we have to show that this is equal to the cotangent of pi over 4n. And so the way we can do that is simply 1 plus cosine of 2 theta over sine of 2 theta is what we're dealing with, and we want to show that that equals cotangent of theta. Now this equals 2 cosine squared theta. This equals 2 sine theta cosine theta. Cancel out the 2 and the cosine theta, and that's equal to cotangent theta as desired. And then a sub n b sub 2n equals a sub 2n squared. I'm sorry, I'm sort of running out of space on this problem. So a sub n b sub 2n. Again, we have these explicit forms, and then these checks basically just come down to trig identities, as we saw with that last one. So we have cosecant pi over 2n, and then this one's going to be pi over 2n cotangent pi over 4n. And we want to show that this is equal to the square of pi over 2n cosecant pi over 4n. So obviously we have these like pi over 2n terms we can cancel. We get an extra 2 here. So this is saying that 2 cosine pi, and I'm just going to replace things by theta here. Sine 2 theta. Oh, and then we have an extra sine theta here. It's equal to 1 over sine squared theta. But of course this is true, because if we use the double angle here, we get a 2 cosine that cancels with the top, and then another sine theta, so that checks out as well. So that problem was also pretty interesting, and this video is probably getting very long. I have yet to decide. I might ask in a community poll if I should upload this full or if I should splice it into different videos. In the cubic equation, okay, so this is just straight plug and chug. Interesting. You know, it might be in the best interest that I don't show this, because this looks very straightforward. Yeah, because this is like, I mean, this is just where P equals Q, and then yeah, I think I'm just going to skip this question for sake of time. Okay, so the functions S and C. Show that S. Okay, so we want 3. Oh, why does it feel like my writing is big all of a sudden? So we have 3S, 3C square root of x. So we're just using the chain rule here, and then we can plug this in. 3s squared x c squared x minus 3c squared x s squared x equals 0. So therefore, and this expression was the derivative d by dx of s cubed plus c cubed. So it's always equal to 0, which means that, what did I just do? Which means that this is a constant, And since s cubed of 0 plus c cubed 0 equals 0 cubed plus 1 cubed equals 1, then s cubed of x plus c cubed of x must also equal 1. I'm starting to notice this is a very interesting problem, just because these sort of look like sine and cosine, but cubed. Show that d. Okay, so this is just some more straight computation. So this is going to be c cubed of x minus s cubed of x. 2c cubed of x minus. So basically, if we add and subtract by c cubed to create this s cubed plus c cubed, that's exactly what we want. So again, this sort of looks like a sort of double angle identity here. So this is a very cool problem. Find and simplify an expression for c terms of c of x for this. So d dx. Okay, so this one we have s prime of x over c of x minus s of x c prime of x c squared of x. This s prime of x c squared, so that's c of x minus, we get a double minus, that becomes s cubed of x over c squared of x. And then combine the fractions, we multiply by c squared over c squared, we get c cubed plus s cubed. And so that's also cool. We get an expression that's sort of like the derivative of tangent is equal to secant squared. This problem is very cool, in my opinion. Alright, now we find the integrals s squared and s to the fifth. So this seems straightforward. S squared of x dx is negative c prime of x dx. So this is going to be negative c of x plus c, right? Yeah. And then for s to the fifth of x dx, that's going to be, we can split off an s squared, which is going to give us that negative c prime, and then we have s cubed, which is 1 minus c cubed dx. And so this is like c to the fourth x over 4 minus c of x plus big C. Because then you can u sub, you can do u equals c of x. So that's very, very interesting. Given that s has an inverse function, okay, so we have 1 minus u cubed 2/3 du. Interesting. So u equals s of x du is going to be c squared of x dx. That's going to give us here 1 minus s cubed is going to give us c cubed to the 2/3 power. That's going to give us c squared. That's going to cancel with the c squared here. So we're just going to get an integral dx, which is x, which is s inverse of u plus c. Also very cool. All right, and the last part, define in terms of u, the integrals here. So let's do this. So 1 minus u cubed to the 4/3. So again, let's consider some sort of substitution like that. Aha, that's cool. Okay, so if we do u is s of x, then we get c to the 4th and then c squared. So this gives us 1 over c squared dx. But we showed earlier that the derivative of s of x over c of x is 1 over c squared. So this is going to give us u over, let's think, the cube root of 1 minus u cubed plus c. Yeah, because if I plugged s into there, that would give me c cubed. Yeah. Wow, that is amazing. Okay. And then we're probably going to use this, maybe? I don't know. Again, we're just going to go with u equals s. Get an integral of c cubed. Okay, so this is going to be wow. Okay, so this is going to be the derivative of s of x, c of x, plus 1 over 2 dx. So that's going to be s of x, c of x over 2 plus x over 2. So that's going to be u times the cube root of 1 minus u cubed over 2 plus s inverse of u over 2 plus c. This is a really cool exercise. That's actually really phenomenal. Wow. Well, so I did skip this problem, but it seems to be just really bashy algebra. So I hope y'all don't mind me skipping it. I mean, here it's just like you literally just have to plug this in, do some garbage, and I yeah, I can't be bothered to do that right now. Other than that, I think there was only one part that I skipped, which was this. I still pretty stumped, but you know, I think for what it's worth, I did a pretty good job for a first attempt. Of course, this is only 1/3 of the whole exam, and you have 3 hours to do it. I haven't been keeping track of the time, so this could be a very lengthy video, but I wanted to go through the work, you know, in detail, or at least in my process, explain my process of solving the problems. So I hope you enjoyed this video. If you made it to the end, thank you a lot for the support, and I'll see you in a future video.